Hello friends, today we are going to learn dynamic programming. Okay, what is dynamic programming? Like earlier we have studied divide and conquer, decrease and conquer. Similarly, we have dynamic programming technique. Okay, and under this dynamic programming, we are having many algorithms to learn, like WARSHALL'S algorithm, Floyd algorithm, knapsack algorithms, and all one by one. So first we are going to see that what is dynamic programming and how we are going to perform the task. First is, why this dynamic programming, right? So it is a technique to solve a problem by overlapping the previous instances solutions, right? Like as you are going and calculating for a Fibonacci number, right? So you are knowing that first two Fibonacci number is 0 and 1. Next will be 0 plus 1 is 1. Right, thereafter 1 plus 1 is 2. So to get the current solutions, we are depends on the previous instances solutions. Okay, previous means just previous one, and it was invented by US mathematicians called Richard Bellman, right? Nearly 1950s, Richard Bellman is invented dynamic programming. Remember one more thing, it is programming is not as we are talking about C programming, C++ programming and all. No, here programming means here talking about the planning how you are going to plan to solve the problem, right? So dynamic programming suggests solving each of the smaller sub problems only once, recording the results in a table from which we can then obtain our solutions to original problem. Yeah, it is very clear that first we are going to solve sub problems and we are recording those sub problems solutions into the tabular form, and from which we are going to obtain solutions to original problem, right? Dynamic programming algorithm design method that can be used when the solutions to a problem can be viewed as a result of sequence of the decision, right? And it works on principle of optimality. What it means, in each and every time our tendency is to find out optimal solutions, right? If you are going to find out the shortest distance, that should be the optimal. If you are going to find out the profit, it should be the maximum. If you are going to find out the distance, it should be the minimum. Okay, so it is working on the principle called principle of optimality, right? Say as we are talking about example Fibonacci numbers, knapsack, shortest path. So one by one we are going to see that what is these examples, right, and how you are going to correlate with dynamic programming. Say as for example Fibonacci number. In this, all of you are knowing that first two Fibonacci number we are going to define. Okay, say Fibonacci of 0 is 0, Fibonacci of 1 is 1. No. If you wanted to find Fibonacci of 2, right, then we are going to say that Fibonacci of 2 is equal to previous two Fibonacci of 1 plus Fibonacci of 0. So what is Fibonacci of 1? It is 1 plus Fibonacci of 0 is 0, hence it is 1. Similarly, now someone is going to find out Fibonacci of 3. So this should be Fibonacci of 3 minus 1, 2 plus Fibonacci of 3 minus 2. Previous 2, right? Fibonacci of 2 becomes Fibonacci of 1 plus 0. Here Fibonacci of 3 becomes Fibonacci of 2 plus Fibonacci of 1. Fibonacci of 2 already we are having values 1 and plus Fibonacci of 1 is 1. Hence it is 2. In similar way, if you are going to find out next Fibonacci number, right? Say you are going to find out Fibonacci of 4. So 4 minus 1 Fibonacci of 3 plus 4 minus 2 Fibonacci of 2. So let us see that Fibonacci of 3 is 2, Fibonacci of 2 is 1, hence answer is 3. Why I am trying to show this is, as we mentioned in the definitions part, we are having solutions to all previous instances and we are recorded in tabular form. So we have already have Fibonacci of 2 as 1, Fibonacci of 3 as 2. Hence, Fibonacci of 4 can be find out with the help of 3 and 2. Suppose you don't have these values recorded. So again you have to solve one by one, because only first 2 Fibonacci number is given, right? Hence, if you wanted to generalize it, what will be general form? If you wanted to generalize it, we can write Fibonacci of n is equal to Fibonacci of n minus 4 minus 1 3, n minus 1 4 minus n minus 1 plus here 4 minus 2 is 2. So we can write Fibonacci of n minus 2. So based on this we can find out, right, all Fibonacci number. But remember that original problems is depends on just previous 2 iterations values in this, right, in the case of Fibonacci number. But if you correlate with this dynamic programming with the help of factorial, then it depends on the only previous iterations outcomes. Okay, so this is one example. Second, if you wanted to discuss factorial, then say if you wanted to have 5 factorial outcomes, this 5 factorial can be written as a 5 into 4 factorial. If you are having the values of 4 factorial in your hand, then definitely we can compute 5 factorial is equal to 5 into 24, hence it is 120. It means we are having the values of 4 factorial. How it will go? Again it will go in similar way. We are having 0 factorial as a 1, hence we are going to define next all n factorial is equal to n into n minus 1 factorial. Same pattern we are going to find out, right, and we can solve it dynamically. So let us see that in this, what is the previous example is Fibonacci number, second is knapsack and shortest path. Remember that when we are talking about the shortest path and knapsack, shortest path. Now, why we are discussing these shortest path examples again in dynamic programming? We already learned this, right, in a greedy method, right? So here we are going to use dynamic programming concepts and we are going to find out with the help of all intermediate vertex, right, which is going to give you the minimum distance, or you can say that shortest distance, depends on the problem scenarios. It means here in dynamic programming we are going to traverse through all possibilities. We are going to make the decision through all the possibilities and finally we are going to conclude that which is the best solutions, or you can call it as a optimal solutions. Say as for example for shortest distance, here we have A, B, C, D. A to B we have a 10 kilometer, B to C we have a, say it is a 5 kilometer, C to D it is again 7 kilometer, and A to D we are having a 20 kilometer, A to C we can call it as a 25 kilometer, right? Say as for example we are having distance like this. Now if you trying to find out A to C, right, A to C, we have direct distance A to C is 25, but there is an indirect distance A to B and B to C. We can find out 10 plus 5 is 15, right? So we are not going with the direct distance, we are going with intermediate distance. For that we'll see that for C how many input edges we have from A. We have A and from we have a B, right? 2 input edge we have. So this is a 5. For that, if you are going to traverse it, B to C there is a path, A to B there is a path, hence A to B, B to C, 10 plus 5, 15 unit, that is there is a path possible from A to C via B, that distance is less, hence we are going to select this path. Like any complex problems we are going to solve, and we are going to learn how exactly you're going to update this weight and you're going to find optimal solutions between the vertices. Now, one more example is knapsack. What is knapsack problem, friend? Knapsack is, call it as a bag. Knapsack is also called bag, or you can say that container. Okay, bag or container. What will happen? We are having the scenarios where there are many items. Say here item 1, 2, 3, 4, and all items is having their own weight. Say it is 20, 10, 15, right, 12, right, and all items is having their profit. Yes, say it is 40, 50, and 45, say it is 60, right. All element is having their weight and profit. Now, we are going to solve the knapsack problem such a way that we are going to generate the maximum profit out of these items. Remember that each and every time here in dynamic programming, we are going to select the complete item. We don't have option to select fractional item. So out of these, we are going to select the item such a way that we are not crossing the capacity of the container. So it means in a program, we have to define capacity of knapsack. That is very, very important. And say as for example, if capacity of the knapsack is already defined, in this case, say it is 35, right? Then you have to select the item such a way that we can have maximum profit in a given capacity called 35, right? Likewise, you are going to solve knapsack problem, right? And here we are going to select the item one by one and we'll see with all the possibilities which possible selection of the element is giving you the maximum profit. And here you can discuss one more things, that suppose you are going to select the item but capacity of bag is 0. If capacity of the bag is 0, it is open bag, say paper bag, right? We are not in a position to keep any item in that, right? Hence, what will be the profit? Profit will be 0. If capacity of the knapsack is 0, then in this case, profit will be 0, right? If capacity bag is very big, okay, say capacity bag is very big, maybe you can call it as, if it is 100 kg bag, you can call it as 100 kg, no problem, right? But there is no item, number of item here in this case we have considered 4, but say in some problem scenarios, we are having big bag, but we don't have any item to keep it, right? Then in that case, again, profit will be 0. Okay? Profit will be 0 if there is no item to select. Profit will be 0. I will give you the real-time scenarios, right, to discuss this knapsack problems. Let us see that what is the difference between greedy method and dynamic programming, right? We have seen that greedy method, right, only one decision sequence is ever generated. Means whatever the decision you make it at the beginning based on the greediness, right, whether A to B is the best choice or A to C is the best choice or A to D is the best choice, will go along with that, right? Here we don't have that. Here we are going to find out with the help of all possible decision. So in dynamic programming, we will be having many decision sequences may be generated, and out of that you are going to find optimal solutions. Like we are going to learn under this first algorithms called WARSHALL'S algorithms. Now, what is this WARSHALL'S algorithm is, right? So WARSHALL'S algorithm is called as, it is used to compute transitive closure for the given digraph. Direct graph is nothing but directed graph. Okay. This is also called it as a digraph, directed graph. And this WARSHALL'S algorithm is called as a, this is the algorithm to find out all possible path between the vertices, right? It means if between the vertex we have 10 different paths, it will give you 10 different paths. right? At the beginning, if there is no path, say we can give as example that if city A to city C, we don't have direct path, but there is a path from city A to city D and city D to city C, right? Then you can say that, yeah, there is a path possible via vertex or city D, A to D and D to C, right? So WARSHALL'S algorithm will find out this kind of path via intermediate vertex, right? Maybe intermediate vertex will be 1 or 2 or 3 more, depends of the problem scenarios, right? But it is going to find out all possible paths between the vertices. Let us see example, right? How you are going to perform the task and when we call it as a transitive closure. So here we have vertex A, we have a B, we have a C and we have a D, right? Say here we have a path from A to B, we have a B to C, a B to D, we have a D to A, right? And here we have a path from D to C. So this is the which kind of graph? It is directed graph. Directed graph. As we discussed that in a program you are not supposed to give this kind of graph. We wanted to convert this graph in the adjacency matrix. And how to find adjacency matrix? Since it is not weighted graph, it is directed graph. There is no weight on edge, right? Hence, just you are writing, if there is a path, you will be writing 1. If there is no path, you will be writing 0. So here, A to B, there is a path. So we are going to write the adjacency matrix. Say, we call it as A, B, C, D, A, B, C, D. A to A, since it is a, source to source, we are going to mention 0. Distance from your home to home is remain 0, or there is a way, if you are going to find out the path, it is remain 0. A to B, there is a path, right? Hence it is 1, right? Then A to C, we don't have direct path. A to D, we don't have direct path. So A to C is 0, A to D is 0. Direct path, we are going to make it out. B to other vertex, B to A, we don't have path. B to B, we have diagonal elements 0. B to C, we don't have direct path. B to D, there is a path. C to all the vertex, C to A, C to B, C to C and C to D, it is remain 0. D to A, there is a path. D to B, no path. D to C, there is a path. D to D is 0. This matrix is called as a adjacency matrix. This matrix is called as a adjacency matrix. Now we are looking for the transitive closure. Remember, the transitive closure is the final outcome after applying WARSHALL'S algorithm. Final outcome after applying WARSHALL'S algorithm. It means it is going to give you all possible paths between the vertices. So, if you wanted to write the outcomes here, I will discuss how you are going to get these outcomes. If you wanted to write these outcomes, how it is going to be? Here A, B, C, D, A, B, C, D. A to A, here you have written 0, but you can see that there is another path A to B, B to D and D to A. Hence, there is a path possible from A to A as well. A to B, it was already 1, so no problem. A to C, earlier it was 0. Now we can see that there is a path A to B, B to D and D to C. So, two intermediate vertex we have B and D. So, there is a path, right? A to B, B to D and D to C. A to B, B to D, A to B and B to D, there is a path, hence it is 1. Similarly, B to A, we don't have direct path, but B to D, D to A, there is a path 1. B to B, again its form cycle, so 1. B to C, there is a path B to D and D to C, right? B to D, there is a path. C to, since C we are having only in degree, right? Edge is terminating at C, there is no outgoing edge from C, hence C to all the vertex is remain 0. D to A, there is a path. D to B via A, there is a path. D to C is 1. D to D, since it is cyclic, D to A to B and B to D is 1. This matrix is called transitive closure. Right? This matrix is called transitive closure. And this is what we are going to get from WARSHALL'S algorithm. You can see, friends, there are many zeros here. Only 1, 2, 3, 4. Only 4 direct edge we had it earlier. Now you can see that 4 plus 4 plus 4, 12 different path we found. A to all the vertex, B to all the vertex, right? And D to all the vertex. Only C, all the inputs are 0. So these outcomes you have to get it after applying WARSHALL'S algorithm. So let us see that how we are going to compute WARSHALL'S algorithm. WARSHALL'S algorithm, again array size is n, comma n. It means what? 1 to n, 1 to n. It is 2-dimensional arrays, right? A to all the vertex, B to all the vertex, C to all the vertex. We require 2-dimensional arrays. Input is adjacency matrix, right, of given graph, and output to be transitive closure of the digraph directed graph. Now here we are having the loop k is equal to 1 to n, first k loop, then I is equal to 1 to n, j is equal to 1 to n, and we are going to do A of ij is a matrix A of ij, or either this, if it is already 1, then it will not go and check these conditions, not required. If this is 0, then we must go and check A of ik and A of kj. If A of ik is 1 and A of kj is 1, then whole it is going to give you 1. Okay. So if there is a path, no need of changing that other side. If there is no path, we must check right hand side part. A of ik, k is intermediate vertex. As I said you, there is a path from A to D and D to C. Right? Here A to D, I to K and K to J. I is a source, J is a destination. So via K there is a path it is going to find. Right? And likewise we are going to implement and we are going to find, all transitive closure. Right? So this statement is very, very important. Remember that A of ij, I is a source, J is destinations. A of ij, or it is logical, or A of ik, I to k distance, and here is k to j distance. K is intermediate row. See, in this part it behaves as a column. Here same k is going to behave as a row. See, ik, I is a row, k is a column. Here k is a row, j is a column. So same k is going to behave as a row as well as column. If you are able to understand this, we are going to solve this problem faster. So let us see that how exactly we are going to perform the task. We have taken that example A, B, D, C, and we have done like this. This is the directed graph, right? And we are having initial adjacency matrix, as we did it, that A to A, B, C, D, A, B, C, D. A to A was 0, A to B was 1, remaining all was 0. B to D was 1, remaining all is 0. C to all 0, and D to A is 1, D to C is 1, remaining 0. So this is the adjacency matrix, we have written it. Now we are going to apply this Warshall's algorithm. Look, first is k is equal to 1. Okay, so for k is equal to 1, you are going to traverse it. First we are going to find out k is equal to 1. If it is k is equal to 1, what are we going to do it? We are seeing that I will start from 1 to n. So k is equal to 1, I is equal to 1, j will repeat. So let us see that k is equal to 1, I is equal to 1, and j will start from 1 to n. Let us see that. In this case, here is a matrix 0, 1, 0, 0, 0, 0, 0, 1, all 0, 1, 0, 1, 0. Saying k is equal to 1, and you can see that in logically it's written in the program a of ik and a of kj. K behaves like a row as well as column. So we are going to select k is equal to 1 means what? K behaves like a row and k behaves as a column. This part we have selected it, right? Where I is a row, j is a column in overall. So now let us see that k is 1, I is 1, j is 1. What will happen? So if you are going to write it, a of ij is equal to a of ij, right, or a of ik, right, and a of kj. If you are writing in a program, you are going to write like this. A of ij, I is 1, j is 1, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. Because we are not going to give A, B, C, D in the program. So by default, we are taking as an array index, right, such a way that you can perform the task faster. So I is 1, j is 1. We are pointing with this. So A of ij is 0. So if A of ij says that there is no path, so we will go and check it in the right hand side. A of ik, I is 1, k is 1. A of 0, 0. So again 0, a of 1, 1 is remains 0. And remember that if in AND operator, if one parameter is 0, then it is going to give you 0 only. Kj, again it is 0. So overall, our answer is 0 and 0 is remain 0, 0 or 0 remain 0, hence it is 0. So you are not going to change anything in this. This positions is unchanged. So just I am writing here resultant 1, right? Similarly, if you go to these positions, what is that? I1, K1, J becomes 2. This part is J becomes 2. So A of Ij, A of 1, 2. A of 1, 2 is non-X iterations. A of Ij is equal to A of 1, 2. A of 1, 2. Right? Remember that a of 1, 2 value is already 1. If this value is already 1, then no need of checking this right hand side. Right? Even if you check, these values are 0 also, 1 or 0 is remain 1, or 1 and 1 is remain 1. So this path is already existed, so we don't have any logical implementation in this program to convert this 1 to 0. No, if it is 0, you are going to find out 1, but if it is already 1, path exists, we are not going to change that. So it is remain 1. Now j becomes 3. If j is 3, then what will happen? If j is 3, a of I 1, 3 is 0, then we are going and implementing this part, right? A of 1, 1 is 0. And a of 1, 3, a of 1, 3 is 0. So 0 and 0 again for this position will be remain 0, no change, right? Similarly, if you go in the last positions, 1, j is 4, 1, 4 is 0. So this part is 0. So we are not going to do anything. So we will go and find out in right hand side. Right hand side, I is 1, k is 1. So 1 1 is remain 0, and if 0 we AND with again 0 is remain 0. So no change. So this is after first iterations, right, where k is equal to 1, I is equal to 1, j is equal to 1 to n. What will happen the next time? We'll be having here k is equal to 1, I is equal to 2, and j is equal to 1 to n. We are going to practice now, right? K is equal to 1, second row we are going to check now. Second row, first values. What is the positions? I, j is, initial value of j is 1, this position. 2, 1, I is 2, j is 1, 2, 1, this position. 2, 1 is 0, right? So we go and check in the right hand side. What is the right hand side? We have ik, 2, 1 is 0, and kj, 1, 1 is remain 0. So 1, 1 is 0. So 0 and 0 become 0. So these positions are not going to change. Right? We can check with this. These positions will be also not changed. Here, these positions also are not going to change. Right? Similarly, this will be remain 1 in k is equal to, right? 1, I is equal to 2, j is equal to 1 to 4. Similarly, when you are going with third case, say what is third case here? K is equal to 1, I is equal to 3, j is equal to 1 to 3. And thereafter I will tell you that clue, right? Clue is, if you are going to find out for these positions, check that. One input is 0, other is 1, it will be remain 0. Check with this position. 1 is 0, other is 0, it will remain 0. Check with this position. One input is 0, other input is 0, and since it was only 1, so no change. Here one input is 0, other is 1, remain 0. 0 and 0 remain 0. If you check for these positions, see here, this 0 and 0 remain 0. Check with these conditions. Here is 1, and this position j value will come as 1. 1 and 1 is going to make it 1. So next iterations you can check that we are going to find out 1. Let us see that. So we got that 0 1 0 0, right? Thereafter all 0 1, all 0 1, this is all 0, and here we had 1 0 1 0, 1 0 1 0, right? And transitive closure, as of now we have k is equal to 1, 0 1 0 0, 0 0 0 1, all 0, right? And this was the shaded part. K is equal to 1. Let us see for this position, then you will understand in better way. Position of this is A of ij is A of ij or A of ik and A of kj. In this A of ij, original value of A of ij, if you see that I, what is the value of I? 1 2 3 4. I is 4. So A of 4, j is, for these positions, j is 1 2 3 4. So j is 2, right? So A of 4 2 is 0. If this is 0, right, and right hand side what will happen? A of ik, I was 4, k was remain 1 for these iterations, and A of 1 and j is remain 2. So this formula we need to apply. So 0, if it is 0, go in right hand side. A of 4 1, A of 4 1. Remember that for this what I said you, if you do like this dotted line, only these values and this value is responsible to change. In that case, look, A of 4 1, what is the value? It is 1. A of 1 2, A of 1 2, what is the value? 1. 1 and 1 makes 1. So 0 or 1, answer is 1. So this value is going to change as a 1. Remaining all, we will check for these positions. This input is 0, this is 1, so it is remain 1 because it was original 1. For this position, this input is 1, this input is 0. So 0 and 1 is remain 0. So no change. So this part we are getting after k is equal to 1. After k is equal to 1. This is the output after k is equal to 1. This is the transitive closure after k is equal to 1. Right? So when you are learning this, it should be A. If you are going for the nth iterations, this value is for the previous iterations. This value is for the previous iterations. Right? And this is again from previous iterations. So this value is from previous iteration n-1. This is n-1. This is n-1. This is for n. It means nth iterations values are depends on just previous iterations values. Similarly, now k is equal to 1, we already filled up. K is equal to 1, we have done with all the rows and all the columns. So what will happen next? Next is going to be k is equal to 2. So when you are going to do the k is equal to 2, what will be our input? Input is the previous iterations outcomes. So this is going to be the input. We forgot about this. Only we are focused on the current outcomes, previous iterations outcomes. So it is 0 1 0 0 0 1 0 0. Now we can do little faster, such a way that we have already understood that concept. 0 0 1 all 0. This is, if k is equal to 1 means second row and second column, second rows and second column we have selected. If you are checking for this position, look, this position, you will go with the shaded part. This input is responsible for this. If you do the cross sections rectangle, this input is responsible. So hence it is 0 and other is 1. Remember that in this part, if both are 1, then only it is going to change the values 1. But here it is not. Hence this value is not going to change. Look, similarly, this is already 1. Here, one input is 1, other input is 0. So it is not going to make any change. Here, one input is 1, other input is 1. Look, this position. Existing value is 0, but there is a path from here 1 to 2 and here is 2 to 4. Hence, this value is going to convert as a 1. Let us see that if you are going to write here 1, 2, 3, 4, 1, 2, 3, 4, this path, right? As you are knowing that 1 is A, B, C, D, we found the values from A to D, there is a path. Earlier it was A to D, there is no path, but A to D there is a path. Look, A to D, there is a path via B. So that is why this value is going to convert from A to D from 0 to 1 because there is a path via B. So we got that. Similarly, if we go on shaded line, that value will be not able to change in shortcuts. Here, one input is 0, other is 0, so this value is not changed. This part, it will remain 0, shaded part. Here, input is 0, another input is also 0, no change. Here, one input is 0, other input is 1, no change. Look, for these positions, one input is 0, other input is 1, no change. Since it is 1, no need of making change. Here is 1. Can you see that? This 0, we will do the cross section here. For this 0, this input and this input is responsible. I am just making round such a way that you can focus on that part. So this and this will be, this 1 and 1 will make it this value as a 1. So let us see that how it is. Basically, we are going for k is equal to 2. K is equal to 2. If you are looking for this positions element, which row it is? 1, 2, 3, 4. So I is 4. If you are looking for the j position, what is the position? 1, 2, 3, 4. It is fourth column, so it is 4. If you are going to apply in the formula, what was that? A of ij is equal to A of ij or A of ik and A of kj. Okay. So let us see that. What is A of ij? Ij 4 4. What is the value of initial value of 4 4? Was 0. Or A of ik. I is 4. K is 2. 4 2. 1 2 3 4. 4 2. What is the value? 1. And K is 2. J is 4. 2 4. Second row, fourth column is 1. Hence, 1 and 1 becomes 1. So, 0 or 1 becomes 1. So, we have seen that only this value and another 4 2 values and 2 4 value is responsible to change this 1. So, after these iterations, this is another transitive closure. And then we are going and applying third row and third column. On this, you are going to apply third row and third column. If you will apply third row and third column, what will happen, friend? Since one of the input of these rows is 0, one of the input of all the rows elements are 0, it is not going to make any change for the next iterations. Remember that, because one of the input part is 0. So 0 and another values, whether it is 0, will remain 0. If it is 1, remain 0 because it is AND property. Both are 1, then only 1. So these iterations, we are not going to get any outcomes. So it will be remain same values, right? Now, if k is equal to 3 is done, then we left with k is equal to 4. If you are writing k is equal to 4 means what? Fourth row and fourth column. In that case, you will see that first values is responsible for this input. So this is 1, here is 1, 1 and 1 makes 1. So finally, we are going to get 1 here. Similarly, here is already 1, so no change. Here is 0. Look, this 0 can be taken from input from same row and same column. 1 and 1 is remain 1. And last is already 1. Similarly, for this position, this input is responsible. So it will be remain 1. For this and this is responsible. So 1 and 1 makes 1. For this position, this input and this input is responsible. So 1 and 1 makes 1. And here is 1. Similarly, here is 0. But if I am seeing that this 0 is, for this 0, we can perform AND operator between input 0 and this 1. So it is not going to make any change. Input 0 and 1 for these positions, we are not going to make any change. Input 0 with AND 1, no change. Input 0 with AND, no change. Right? So all 0. And here last row is all ones. So basically this, what you are getting now is called final transitive closure after applying WARSHALL'S algorithm. All ones except from vertex C. And that is what we have discussed in that example part before, that we will be getting the outcome like this. And this is called transitive closure, and it will give you path between the vertices, all pair path, right? All possible path between the vertices. Now, so let us discuss that summary of this. So dynamic programming works on principle of optimality, and dynamic programming have many decision sequences, right? As I said that it's not like greedy, we can generate many sequences, and out of that you are going to find out final outcomes. And then transitive closure is to find all possible paths between the vertices, right? So this is all about your summary of WARSHALL'S algorithms, and we'll stop here. Thank you very much.